Though I say that working with the entire residual vector, all those n numbers, is always the best way to go about checking the goodness of fit of your model, still people keep on searching for one magic number, using which, just using that single number, you want to assess the goodness of fit. And certain such measures have been proposed in the literature. Now the best advice that I can offer about them is do not use those numbers. It is never possible to assess the complicated thing like goodness of fit of a model by merely looking at a simple number. But since those things are anyway popular, it's a good idea to have some knowledge about how they work. Now all those techniques are primarily based on our familiar picture where we have the column space of X and we have our data vector Y, and we are projecting this data vector orthogonally onto column space of X. Then you can easily feel that the distance of this from the column space of X, that should reflect in some way how good the fit is. So the natural choice is to look at this vector. So the natural choice is to look at this error vector, this residual vector, and how large this vector is. Now my suggestion was look at the vector in its full glory. It consists of n numbers, where n is the ambient dimension. In this case it is only 3. But whenever you try to make one summary number, you generally work with the length of this residual vector, just this single length. Now there are various ways by which you can use it. Possibly the simplest is just to look at the length and scale it appropriately to get an unbiased estimator of sigma square. Sigma square hat is nothing but squared length of this divided by a suitable degree of freedom. So use that as a way of measuring the precision, how good the fit is. Not a very good idea, because if you just change the unit of your entire problem, then that number also shrinks and grows accordingly. But surely you do not say that if I just change my unit from centimeter to inches, you surely do not want to say that it has become more precise. Or if you move from centimeter to millimeter, things have just become 10 times less precise. You do not want to make such a statement, but still people do quote this sigma square hat as a rough guideline as to how much plus minus you expect. So that is type 1. Now the type 2 things are kind of working on this idea of this squared norm of this vector, but scaling it down so that it becomes phi of unit. Now how that scaling is done, that takes us into somewhat deep linear algebra, not deep linear algebra, but some amount of linear algebra that we are going to go into next.